Hello, this is Dr. Toller. The purpose of this video is to introduce you to a process of creating an Excel spreadsheet that can be used to solve a linear programming problem. Now, there are a lot of different ways to do this. I have laid out one way of setting up this spreadsheet. I encourage you to try this setup so that you can see how it's done and how you can use it to solve a linear programming problem. But if you like a different layout or different wording, different formatting, feel free to create the model that suits you best. I have selected a problem from Chapter 7, a generic two-variable linear programming problem that could be solved graphically because it only has two decision variables, and simply to illustrate how to set up the spreadsheet. And I'm going to talk you through the scenario just so that you know how the problem is done. So the scenario is we have a salsa manufacturer. They produce two brands of salsa, Western Food Salsa and Mexico City Salsa. I'll move this over so you can see it better. And they want to know how many jars of each brand of salsa they should produce in order to maximize their profit. And we're going to let W be the number of jars of Western Food Salsa and the number of jars of Mexico City Salsa. And we're also told in the problem that we can make $1 of profit for every jar of Western City Salsa that we produce, and we make $1.25 for every jar of Mexico City Salsa. And of course the assumption is we can sell all the jars that we produce. And we're also told that the units or the constraints are in ounces. And during the course of the problem, they also tell us that they have a limited amount of ingredients for these two types of salsa. They've got whole tomatoes, tomato sauce, and tomato paste. And we have 4,480 ounces of whole tomatoes. We have 2,080 ounces of tomato sauce. And we have 1,600 ounces of tomato paste. And we're also told that to make a jar of Western Food Salsa, it takes 5 ounces of whole tomatoes, it takes 3 ounces of tomato sauce, and 2 ounces of tomato paste. And respectively, for the Mexico City Salsa, it takes 7 ounces of whole tomatoes, 1 ounce of tomato sauce, and 2 ounces of tomato paste. So, with that information, we can create our objective function, which is 1, in this case it's $1, times the number of jars of Western Food Salsa plus $1.25 per jar times the number of jars of Mexico City Salsa. So that's the objective function that we want to maximize. And then of course we would write 3 constraint equations for each of the 3 ingredients that we have a limited quantity of. And in all 3 cases, the amount that we use has to be less than or equal to the total amount of ingredients that we have. So, the whole tomatoes constraint is 5 ounces per jar of the number times the number of jars of Western Foods plus 7 ounces per jar times the number of jars of Mexico City Salsa. That has to be less than or equal to 4,480 ounces of whole tomatoes. Likewise, the tomato sauce constraint is 3 ounces per jar times the number of jars of the Western Food Salsa plus 1 ounce per jar times the number of jars of Mexico City Salsa. That has to be less than or equal to 2,080 ounces of tomato sauce, which is all we have. Lastly, 2 ounces per jar times the number of jars of Western Foods plus 2 ounces per jar times the number of jars of Mexico City salsa has to be less than or equal to the 1,600 ounces of tomato paste that we have. And lastly, the non-negativity constraint is M and W have to be greater than or equal to 0. Now, because I took this from the book and we know what the answer is already, we know that the optimal solution should be 560 jars of Western Foods salsa and 240 jars of the Mexico City salsa, with a optimal solution of $860 of profit. And of course, whenever you're developing a model, it's always a good idea to start with the creation of the model and test it with a problem that you already know the answer to. So let's take a look at the layout. And there is no magical meaning to the fact that I started in column E. I just like to always leave some blank columns to the left in case I want to add some additional information off to the left. But you can start in column A if you like. It's entirely up to you. The references, the relative positions will be the same. So, in the very first row, I have a row for the name of the variable that I'm using. And as you can see, I've added a comment here to remind myself what goes in this column. I don't have comments throughout, and those of you who are familiar with Excel should know that if you want to add a column, you can click on the Review tab, and you can add a new comment wherever you happen to have the cursor. I don't really need a comment right now, so I'm just going to go back. But oftentimes comments are good just to remind you of how the model is set up and how it's used. Okay, I only have two variables, so I'm just going to put in the two variable names here. And I've given myself some directions off to the left. And in this next row, I'm going to put the coefficient values for my objective function, which in this case are 1 and 1.25. All of this information will simply be the coefficient values for my objective function and for my constraint equations. So obviously, you need to do this type of model setup on a piece of paper before you enter in the information. I strongly advise you to write all this out before you start putting these numbers in to help you keep the information straight. So I've set up, in this case, actually 4 rows for the constraints, even though I only have 3 constraints for this particular problem. That way I can simply type in the coefficient values for each of the constraint equations. So this 5, 3, and 2 comes from the constraint equations, the coefficients on each respective variable in each coefficient, in each constraint equation. So that's my 5, 3, and 2. I'm going to have 7, 1, and 2. As well. I don't have a third value here, so I'm just going to leave those blank. But just to highlight the fact that I'm not using these values, I'm going to make them all 0. The right-hand side resource limits for whole tomatoes, tomato sauce, and tomato paste, I'm going to put out here. I don't have to have this blank column, but I left it there just so that if I expand this model to include 2 additional variables, I already have the space to do that. but I'm just going to type in the values for the right-hand side resource limits. So I've simply put the values from my model in this upper area. And I can use these values in calculations that take place further down. You see here I had a problem with my spreadsheet. I want this variable name from this position to be placed here. So I'm going to type an equal sign, click on that cell, press enter, and that value will be brought down. That way, whenever I change this value here, for example, if I wanted to identify that as being Western, it would update the decision variable name down below. Those are just little extras. They aren't absolutely necessary. You could just as easily use W or M. All depends upon how much information you want to give. Okay, now I've identified the location for my decision variables. These are locations where the final solutions will be placed by the Excel program, linear programming program. I can leave these at 0. 0 doesn't often pose a problem for the program, but sometimes it does. So to be safe, I usually start my linear programming solutions off with a value of 1, an initial value of 1. And then we're going to have an area for the objective function calculation. And we know that the objective function calculation is 1W plus 1.5M. I've already typed this equation in. Let's make sure it's the right equation. So I'm going to take 1, which should be G5 in this case. So this needs to be G5. I've been working on this before, so that's why some of these values aren't correct. But what I want is the value in G5, which is the coefficient on the first decision variable in the objective function. So I want to take that 1 and multiply it by the number in the decision variable cell, which in this case is G12 for me. It's a good idea to look at the function area up here where you can see the equation. Might be a little small on your screen, but if you want to zoom in, I think you can. So I'm going to take this 1 and multiply it by the number of jars, and then I'm going to add to that the coefficient on M, multiply that by the number of jars of M, and since I've set this up for 3 variables, I actually have I5 times I12, but both of those are 0, so they're not going to factor into this particular problem. So as you can see, that's how you can actually set up a model that can handle more variables than a particular problem may have. In this case, we only have 2 variables, but I have this model already set up to handle 3. So by putting zeros in there, I don't have a problem. And you can see the initial value of the objective function is going to be 1 times 1 plus 1.25 times 1, which is 2.25. Now that's just the initial value of my function. At least that way I know the calculation is being performed correctly. Now, the next thing you want to do is program in your constraint equations, which are these equations here, out in my case, n, 11, 12, and 13. So the calculation here, if you double click, it will actually show you the equation and show you the values being used in each calculation. So it's going to take the value in G6, multiply it by the value in G12, and then add to that the product of H6 times H12. And again, because I have this set up for 3 variables, it's going to take what's in I6 and multiply it by the value in I12. But again, since this is 0, that term will go away in this particular problem. So what's being done is the calculation 5W plus 7M. We're going to make that less than or equal to that right-hand side constraint. Now, this inequality is just something that I type in to remind myself of what the relationship is. So for this problem, I would literally type less than or equal to. These don't factor into the actual solution calculation. It's just a reminder to me of what the relationship is when I set up the problem in the Excel linear programming solver function. And for the right-hand side, I typed in equal sign K6 so that it pulls whatever I type in up above in K6 and places it in that cell. And I do the same thing for each of the resource limits. That way I don't even have to retype them. And let me go back to this first constraint equation, and what you can see is when I typed in that constraint equation, I put a $ in front of the column and the row reference in order to anchor this cell value, so that, and I did that because I'm simply going to copy this equation down to the other constraint equations. And because I didn't anchor the first value, G6, when I copy it down 1, it will increment from G6 to G7, but it won't change the G12 cell reference. Now, obviously, you can just type these in yourself. So for the second constraint, we're taking the coefficient for the second constraint equation. In this case, it's 3. We're multiplying it by the value in the decision variable cell, which is still G12. And we're adding to that the value in H7, which is 1 in this case, which is the coefficient on M in that second constraint equation. We're multiplying it by the value in the decision variable for M. And again, I've set this up for 3. I'm not using the third variable, so that 0 will simply cause this third term to go away, and it's not going to be a problem. So I did this And I anchored those cells so that way I can simply copy down those equations, and it will change the coefficients on the decision variables and perform the calculation that I need for that constraint. So when you set up your problem, it should look like this. So I'm going to pause here and give you the opportunity to construct this Excel spreadsheet using these relationships. You can run the video back if you need to check any part of the steps that you need to go through to build this. And I'll have a second video that shows how to use this to solve the problem.